SwayamPrabha. Digital India. Educated India.
Hello everyone, welcome to lecture 10. So, we will continue with the Mohr circle. Okay. Let us have a quick recap of what we did in the Mohr circle. You can recall this square on which we had drawn the components of the stress matrix. So, this is the E1 direction and that is the E2, then coming out of the paper is E3 and we have sigma ZZ acting on E3 plane, which is the face of the paper. So, E3 is the face of the paper, on E1 plane we have sigma XX and tau xy. Similarly, on E2 plane we have sigma yy and tau xy. Given this, we wanted to find out the sigma and tau on a plane which is at an angle alpha counterclockwise from E1 plane. So, that plane we drew with the blue line, and that is the normal to this plane n, which makes an angle alpha from E1 axis. So, this angle is alpha and I want to know sigma and tau on that plane. So, we figured out that the sigma was equal to sigma xx plus sigma yy by 2 plus radius r times cosine of 2 phi minus 2 alpha. Then the shear traction tau was equal to r times sine of 2 phi minus 2 alpha, where r equals square root of sigma xx minus sigma yy by 2 whole square plus tau xy whole square, and tan of 2 phi is equal to 2 times tau xy over sigma xx minus sigma yy. All right. So, this formula is everything here is in terms of the sigma matrix corresponding to this coordinate system, which looks as follows. Sigma xx, tau xy 0, tau xy, sigma yy 0, 0, 0, sigma zz, and such a stress matrix will arise when the third coordinate axis is also the principal axis, right. That is why we have 0 on the third column. All right. So, given this formula, we could see that sigma and tau on any arbitrary plane alpha forms a circle. If you start making dots for all the alphas, you get a circle, right, and that is called the Mohr circle. All right. So, let us draw that Mohr circle. So, we have sigma x x, sigma y y. The center of the Mohr circle is at the midpoint of those two. So, that is the center. And then the point corresponding to E1 plane has coordinate sigma x x comma tau x y. So, you join the center with the E1 plane point and you get the radius. So, with the center and the radius known, you can now draw the Mohr circle. All right, so that is the Mohr circle, and then this angle is 2 phi, and if we want to get the traction on plane which makes an angle alpha from E1 plane counterclockwise alpha, then on the Mohr circle we go 2 alpha, but clockwise, right. So, we go 2 alpha clockwise, and then this point over here, that is the alpha plane, the sigma and tau for alpha plane, very simple. Okay, that was the Mohr circle, and then we said with this Mohr circle we can extract the information of principal stress components, tau max, and we also saw that their values were matching with our mathematical derivations earlier. For example, this is lambda 1 and the other extreme is lambda 2, such that lambda 1 is equal to sigma x x plus sigma y y by 2 plus the radius, and lambda 2 is equal to sigma x x plus sigma y y by 2 minus radius. This also tells you that the radius is actually lambda 1 minus lambda 2 by 2, because lambda 1 minus lambda 2 is the diameter, divide by 2 you get the radius, and but radius is also equal to tau max. So, tau max is then equal to lambda 1 minus lambda 2 by 2, which we had derived, and the sigma on the plane having tau max, which you can see is the top point here, right. So, the sigma on that plane is the sigma corresponding to center of the circle, which is sigma x x plus sigma y y by 2, which is same as lambda 1 plus lambda 2 by 2, right. So, this coordinate in terms of principal stress components becomes lambda 1 plus lambda 2 by 2 comma lambda 1 minus lambda 2 by 2, right, very simple. So, at what angles are the principal planes from x plane? So, you can see from the Mohr circle, this point is the x plane, and we have to go 2 phi clockwise in the Mohr circle to get to the plane where we have lambda 1 acting, right. So, that means in your original coordinate system, like in this square diagram, we have to go phi anti-clockwise, isn't it, to get to the first principal plane, because in the Mohr circle from the x plane we have to go by 2 phi clockwise. Therefore, in the actual coordinate system we have to go by phi, half of that angle phi, but in the opposite direction, that is anti-clockwise, right. So, we could write that here also, the angle for first principal plane that is phi anti-clockwise, right. From E1 plane or x plane. And if you want to get to the second principal plane, then in the Mohr circle you have to go 2 phi plus 180 degree. So, in the actual coordinate system you have to go by phi plus 90 degree, right. So, the angle for the second principal plane is then phi plus 90 degree anti-clockwise. From E1 plane. Do you recall how to get the principal planes and principal stress components? You have the sigma matrix and you have to solve for the eigenvalues and eigenvectors, right. That sigma matrix is a 3 cross 3 matrix. To get the eigenvalue, you have to solve a cubic equation. The characteristic equation of that matrix is a cubic equation. Solve the cubic equation to get the 3 eigenvalues and then find out the eigenvectors. So, that is a really complicated process. You have to know how to solve cubic equation. Of course, you should know that, but it is a bit difficult. Whereas, in the Mohr circle you see everything is so easy. You could graphically tell where is the first principal axis, where is the second principal axis, what is the value of the principal stress components, what is the value of tau max, where is the plane corresponding to tau max, everything you can tell very easily just from the graph, right. So, that is the advantage of Mohr circle, but remember its limitation, that one of the principal axis must be aligned with the coordinate axis, right. Only then the stress matrix has this particular form, and then only your analysis works. If you have a general stress matrix, Mohr circle does not work, right. So, your E3 here, for example, the E3 coordinate axis is to be aligned with the principal axis. Similarly, there could be an example where E1 coordinate axis is aligned with the principal axis, and we can still do the Mohr circle business, or if the E2 coordinate axis is aligned with the principal axis, then also we can do the Mohr circle business. So, one of them has to be aligned with the principal axis. Okay. All right, let us work out an example. This was theory. Let us work out an example. So, suppose that the sigma matrix for a given coordinate system has the following form. All right. So, you can see from the stress matrix form that we can certainly apply Mohr circle idea, is not it, because the E3 axis here is aligned with the principal axis because of the nature of the stress matrix. So, we can use Mohr circle. So, I will write here, we can use Mohr circle since E3 axis or the third axis is also the principal axis. Alright, so if that is the case, let us try to draw the Mohr circle. So, sigma x x here is 4 root 2, sigma y y is 8 root 2 and tau x y is 2 root 2, right. So, if we draw the Mohr circle, we have the sigma tau plane. So, we first write down sigma x x 4 root 2, sigma y y 8 root 2, and then the center, which is the midpoint at 6 root 2, and then the point corresponding to E1 plane. On E1 plane we have 4 root 2 and 2 root 2. So, the tau is 2 root 2. So, let us say it is somewhere here. So, that is 2 root 2. Now, we can join the center and the point corresponding to E1 plane, and that becomes our radius, right. So, for this triangle that we have here, the vertical line is 2 root 2 and the horizontal line, that is also 2 root 2. Right. So, what is the radius then? 2 root 2 square plus 2 root 2 square and under root, which turns out to be 4 in this case, right. So, with 4 as the radius, we can now draw the Mohr circle. Okay, that is the Mohr circle, and then the question is, where are the principal planes, where is the plane corresponding to maximum shear stress, and what are the values of the principal stress components and the maximum shear stress, right. So, all those things can be very easily taken from this diagram, is not it. For example, what is the value of lambda 1? So, that could be the center plus the radius, right, and center minus radius. So, lambda 1 comma 2, they are 6 root 2 plus minus 4, is not it. What about tau max? So, tau max is nothing but the radius, which is 4. Where is the plane corresponding to the principal plane having principal component equal to, let us say 6 root 2 plus 4. Okay. So, if I want to know the angle for plane corresponding to this point, so angle from E1 axis for this principal plane, it is a principal plane because there is no tau, right. So, how much is that? So, from the x plane we have to see how much do we have to rotate. So, that is the x plane, and this is what we have to rotate. So, what is that angle? So, you can very easily see that this angle is 45 degree, right, because x side is 2 root 2 and y side is also 2 root 2. So, it is an isosceles right triangle. So, angle is 45 degree. Therefore, this angle is than 135 degree. So, on the Mohr circle we have to go 135 degree clockwise, right. This means in the actual coordinate system we have to go 135 degrees by 2 counterclockwise. Okay. So, I will write here that is 135 degree by 2 counterclockwise. Similarly, you can tell what is the angle corresponding to second principal axis, right, or second principal plane. How about tau max? By what angle should I rotate to get to the plane having tau max? So, this is the point for tau max. And how much do I need to rotate? So, this angle, that is 45 degrees. So, this means for tau max, for tau max plane I have to go 45 degrees by 2 counterclockwise. All right. So, things are quite easy, is not it, with Mohr circle. Okay. So, with this I will close the Mohr circle concept. There is another very nice concept of Mohr's stress plane. Okay. This is Mohr's circle, but there is also something called Mohr's stress plane. Let us see what that is. Okay, so, suppose that the stress at a point is such that the 3 principal stress components are lambda 1, lambda 2, lambda 3, okay, and in the decreasing sequence lambda 1 greater than lambda 2 greater than lambda 3. So, the stress matrix corresponding to the principal coordinate system is going to be diagonal, right. Now, with this information we ask, if I take any plane at that particular point, we get some sigma and tau, right. And I start putting dots corresponding to those sigma tau on the sigma tau plane. So, we again have sigma tau plane, stress plane, but now we do not confine ourselves to planes whose normal is perpendicular to one of the principal axes. We want to take all the planes, all right, and I start putting dots. So, what kind of picture am I going to get? That is the question. Suppose I take planes whose normal is perpendicular to E3 axis, okay, the third coordinate axis. So, for those planes, if you start putting the dots, what will you see, right? So, if you start putting lambda 1, lambda 2 and lambda 3, then the Mohr circle corresponding to the planes whose normal is perpendicular to the third principal axis will be passing through lambda 1 and lambda 2. is not it? So, that is lambda 1, this is lambda 2 and this is lambda 3. Similarly, if you take Mohr circle corresponding to planes whose normal is perpendicular to first principal axis, then the Mohr circle that you get will have lambda 2 and lambda 3. So, you get something like this, right. Then you have another option, take the planes whose normal is perpendicular to second principal axis, then that Mohr circle will have lambda 1 and lambda 3 as its principal stress components. So, it is going to pass through lambda 1 and lambda 3 and that is the biggest circle here. All right. So, see these 3 circles correspond to very special directions, right. So, I could write here that this one for example has got the direction such that the second one is 0, right. If you write down the normal vector in the coordinate system of principal axis, that is how it will look like. For this one, the normal vector is going to look like 0 star star, whereas for this one the normal vector is going to look like star star 0. So, these normal directions are very special. What about any other arbitrary direction? So, where will the dots be? So, it turns out you can do some mathematics and show that the dots are going to fill these areas. Okay. The region within the 2 inner circle is forbidden, all right. So, you start putting all the dots, the shaded region gets filled. So, that is the Mohr's stress plane. So, I can write here that sigma tau for arbitrary planes occupy the shaded region. Now, can we see whether this principal stress components are they minima or maxima? You remember we set the derivative equal to 0 and then we get the eigenvalue problem, because we are trying to find the maxima or minima normal traction, is not it? So, we got the eigenvalue problem and we got 3 solutions and we said they should be either maxima or minima. Now, here is the diagram where you have sigma tau for each of the planes. What can you say now, are they maxima or minima? Lambda 1 for example, what is it? Is it maxima or is it minima? So, this turns out to be the global maxima, is not it? Because it is higher than all possible sigmas. So, this is the global maxima, whereas lambda 3 that is the global minima. And what about lambda 2? you see lambda 2 is neither maxima nor minima. Is it even a local maxima or local minima? So, for that in the local region also it should be either maxima or minima. See, if you go above the point lambda 2, you get the region which has higher sigma as well as lower sigma. You go just above point lambda 2 or just below lambda 2, right. You see this circle here, and in this region is lambda 2 minima? No, because you have points there where sigma is more than lambda 2. You also have points where sigma is less than lambda 2. Now, you can shrink that circle also, still that statement is valid. So, lambda 2 is neither local maxima nor local minima, it is like a saddle point. Okay. But lambda 1 is the global maxima and lambda 3 is the global minima. So, I could write that now, that lambda 1 is the global maxima, lambda 3 is the global minima, and lambda 2 is certainly neither global maxima nor global minima, but it is also not a local maxima or minima. Not a local max slash mean either. So, it is a saddle point. See, you got these solutions by just setting the first derivative equal to 0. So, when you set the first derivative equal to 0, you are not guaranteed to get maxima or minima, you can also get a saddle point. Okay. That is why you got this lambda 2. What can you say about tau max now? Look at the diagram. So, you had 3 of them, right, lambda 1 minus lambda 2 by 2, lambda 2 minus lambda 3 by 2, and lambda 1 minus lambda 3 by 2, right. Can you see those points? So, if I take the green dot, here are those points. So, this is for example lambda 1 minus lambda 3 by 2, then this dot is lambda 2 minus lambda 3 by 2, and then this dot is lambda 1 minus lambda 2 by 2. Now, what do you think? Is it global maxima, global minima, local maxima, local minima? So, certainly lambda 1 minus lambda 3 by 2, that is a global maxima, is not it? Now, what about other points? Are they minima? Is it a global minima? Where is the global minima? Where is the global minimum? So, that is where tau is equal to 0, right. If you only check for the magnitude of tau, then the global minimum is when tau is equal to 0. So, of course, these points are not global minimum. Is it local maximum? Do you think it is a local maximum? You can again go by that argument of drawing a small neighborhood about the point, and you will see that it is not. It is not a local maximum, neither it is a local minimum. Okay, it is just some kind of saddle point. All right. Okay, very good. So, I hope you got some idea about stress at a point and what are the various combinations of sigma and tau which is possible. There is another very interesting situation just think of what happens to this diagram when two of the eigenvalues become the same. Let us say lambda 2 becomes equal to lambda 3, what happens then? So, I will write here what happens if lambda 1 greater than lambda 2, but equal to lambda 3. Can you see what is going to happen? Just look at this diagram, lambda 2 equal to lambda 3. So, that circle shrinks to a point. Just think of letting lambda 3 go towards lambda 2. See, that circle is going to get smaller and smaller and smaller, and finally, what do you have? You will have just one circle corresponding to lambda 1 and lambda 2. So, in that case, the stress plane reduces to a circle where this is lambda 1 and this point has lambda 2 equal to lambda 3, and all sigma tau will only lie on this circle. Okay. See, you can get this from the general picture. Let lambda 3 go to lambda 2 and you will see how the diagram is shrinking and finally changing to a circle. There is another situation. What happens if lambda 1 is equal to lambda 2 is equal to lambda 3? The three principal stress components are the same. So, can you see what is going to happen now? The whole region simply shrinks to a point, is not it? So, it shrinks to a point. So, in that case you take any plane and you only have sigma equal to lambda 1, tau equal to 0 on all the planes. And can you recall what is that situation? You remember we had discussed earlier the state of stress matrix in a fluid which was in static equilibrium. So, in case of fluids, all the planes have only pressure acting on them, right. So, this is that situation, which is also called hydrostatic state of stress, okay, because fluid in static state, hydro. So, this is also called hydrostatic state of stress. All right. Okay, so that is about the Mohr circle. Now, there are many small concepts remaining for the stress, which I will try to finish, okay, and then we will be done with stress, and after that we will start talking about strain. Okay. So, let us finish those small topics for stress. The first one is stress invariance. So, here we know that as the body gets deformed, the stress tensor at a point has got some value, and you change the coordinate system, stress tensor does not change, but the corresponding stress matrix changes, right. And we have also found out how do the stress matrix transform from one coordinate system to the other coordinate system. So, stress matrix changes, but the stress tensor itself does not change. and the change of stress matrix we had figured out was given by this formula, sigma hat was equal to the rotation tensor matrix transpose into sigma into R, right. So, that is how you can relate stress matrix in one coordinate system to the other coordinate system. We want to know, as this stress matrix changes, there must be something which does not change. Of course, the individual components of the matrix is changing, sigma x x is something, sigma x x hat is something else. The individual components are changing, but maybe combinations of the components may not be changing. For example, we have learned the concept of principal stress components, right, which you can get from the eigenvalue of the stress matrix. So, suppose at a point we have the stress tensor, you find the principal stress component. Now, you change the coordinate system. So, you have different stress matrix, again you find the principal stress components from the eigenvalue of the new stress matrix. So, do you think the eigenvalue will be different or the principal stress components will be different? Will the principal planes be different? See, they are physical quantities, principal planes, principal stress components, they are independent of coordinate system. So, when you find eigenvalue from one stress matrix and then eigenvalue from the new stress matrix, both should give you the same value, because the eigenvalues have got a physical meaning of principal stress components, right. So, the eigenvalues are something which are invariant. So, basically the principal stress components, they are invariant. Okay. Even if you change the coordinate system, stress matrix changes, but the principal stress components will not change. All right. So, I can write here, although the stress matrix changes, but the principal stress components or the eigenvalues, right, should not change. So, they are invariant. So, that is one set of invariants, the eigenvalues do not change. And how do we find eigenvalues? We find it from the characteristic equation, right. Can you recall? So, for the eigenvalue, the equation is sigma times x is equal to lambda times x, is not it? That is the eigenvalue eigenvector equation, which you could also write as sigma minus lambda times identity times x is equal to 0, right. And then we say, for this equation to have non-zero solution, the determinant of the matrix should be equal to 0, right. So, we say that the determinant of the matrix sigma minus lambda times identity, that should be equal to 0. And this, when you find out the determinant, you get a characteristic equation, which is a cubic equation in the eigenvalue lambda, is not it? And that cubic equation you solve and get the eigenvalues. So, you see this equation you can get once from the sigma matrix and another time from the sigma hat matrix, and in each of the cases, because the eigenvalues have to be the same, the characteristic equation should also be the same, is not it? Which means when you say determinant of sigma hat minus lambda times identity equal to 0, both of them should give you the same characteristic equation, because they have the same eigenvalues, right. So, let us plug in the formula for sigma hat and see what do we get. So, determinant of sigma hat, which is R transpose into sigma into R minus lambda into identity, and let us write identity as R transpose into R, because R is a rotation tensor. So, R transpose into R is an identity, right. Remember from the first class, R transpose into R. So, that is equal to 0, which we can also write as determinant of R transpose into sigma minus lambda times identity matrix into R matrix equal to 0. Can you see this? I took the thing inside as common. See, when you work out, you will get what's there in the top. Pre multiply by R transpose, post multiply by R, you will exactly get the expression that's there in the top, right. And then you know that determinant of product of matrices is same as the product of the determinant of matrices, right. So, then we get determinant of R transpose into determinant of sigma minus lambda times identity times determinant of R equal to 0. But now, since R is a rotation matrix, its determinant is equal to 1, right. Remember from the first class. So, that means this finally becomes determinant of sigma minus lambda times identity matrix equal to 0. So, you see we started with the determinant of sigma hat minus lambda times identity, and we could show that this is going to give us same thing as determinant of sigma minus lambda identity. So, basically they have the same eigenvalues. All right. Now, let us expand this expression determinant of sigma minus lambda identity and see what we get. So, this is basically determinant of sigma 1 1 minus lambda, sigma 1 2, sigma 1 3, then sigma 1 2, sigma 2 2, sigma 2 3, sigma 1 3, sigma 2 3, and sigma 3 3, right. And on the diagonal you have minus lambda, that is equal to 0. And when you work out the determinant, you will get minus of lambda to the power 3 plus lambda square into sigma 1 1 plus sigma 2 2 plus sigma 3 3 minus lambda into sigma 2 2 sigma 3 3 plus sigma 1 1 sigma 3 3 plus sigma 1 1 sigma 2 2 minus sigma 1 2 square minus sigma 1 3 square minus sigma 2 3 square plus determinant of the sigma matrix equal to 0. So, this is the equation that you get. Okay. So, this is the characteristic equation. Which is cubic in the eigenvalue. You have to solve for cubic equation, you have to know how to extract roots from them, all right. And sometimes cubic equation have real roots, sometimes it has imaginary roots also. But because this equation corresponds to our physical stress matrix, for which we know that it always has 3 principal stress components. So, the roots here are always going to be real. Okay, you will always have 3 real roots. Anyway, the point is, you see this characteristic equation written in terms of the components of the sigma matrix. You could also have written it in terms of the components of sigma hat matrix, right. The all components simply get replaced with sigma hat, but because they have to give you the same eigenvalue. So, what does that mean? The coefficients must be the same, is not it? Then only they give you the same eigenvalue, is not it? Which means the coefficients here are also the invariants. Okay. So, basically this coefficient is also an invariant, and it is called, it has got a name that is called I1. This coefficient that has got a name, and it is called I2, and this coefficient is called I3. So, I1, I2, I3 are invariant. So, you have the stress matrix, take the sum of the diagonal entries sigma 1 1 plus sigma 2 2 plus sigma 3 3. In the second case, you will have stress matrix sigma hat, then you have diagonal entries sigma 1 1 hat plus sigma 2 2 hat plus sigma 3 3 hat. So, both should give you the same value. So, I1, because it is invariant, that means I1 would be equal to sigma 1 1 plus sigma 2 2 plus sigma 3 3, which is same as sigma 1 1 hat plus sigma 2 2 hat plus sigma 3 3 hat. All right. Can you think of what does this invariant become when the stress matrix is written in the principal coordinate system? So, in the principal coordinate system, the stress matrix is diagonal, the entries are lambda 1, lambda 2, lambda 3, right, off diagonals are 0. So, what do you get? So, in that case I1 would be what? The sum of the diagonals, which is simply lambda 1 plus lambda 2 plus lambda 3. What about I2? What will be I2 in that case? Look at the expression for I2 here. You do not have the off diagonal component, the shear components are not there. So, you only have the first 3 terms then, right. So, you will get lambda 1 lambda 2 plus lambda 2 lambda 3 plus lambda 3 lambda 1. For I3, since I3 is determinant, and if you have a diagonal matrix, what is the determinant? It is simply the product of the diagonal entries, right. So, in this case it is lambda 1, lambda 2 and lambda 3, right. Can you now see the structure? For I1, take each of the roots and add them. For I 2, take pairs, get the product and sum. For I 3, take triples, and since there is only one triple, so you have just one term, lambda 1, lambda 2, lambda 3. Okay. So, those are the invariants in terms of the principal components, and in terms of a general stress matrix also you have the expression, right. Okay. So, that is about the invariants of stress matrix. All right, there is also something called octahedral stress components. Okay. Octahedral stress components. So, first of all you have to think of what is octahedral plane. So, basically they are the faces of a octahedron. Octahedron is a 3D body having 8 faces, okay, and the normal to those 8 faces have the following form. The normal n vector has got the following form: plus minus 1 by root 3, plus minus 1 by root 3, and plus minus 1 by root 3. So, basically they are equi-angled from the coordinate axis. Therefore, the 3 direction cosines are of same magnitude, and you can see how many are there. For first component 2 into 2 into 2, 8 faces. So, you get an octahedron, all right. And there is a very nice formula for the normal traction and shear traction on octahedral planes, okay, which we are going to work out. So, let us suppose our coordinate axis is now again the principal coordinate system. Okay. So, we have principal coordinate system, and then we think of octahedral planes with respect to principal coordinate system. So, think of octahedral planes relative to principal coordinate system. So, with respect to principal coordinate system, the n vector will look of the form as given here, right. So, what will be sigma on the octahedral plane? So, we know sigma is equal to the sigma matrix times the vector n, and then you dot with the vector n, right. And let us write each of them in the principal coordinate system. So, we have lambda 1, lambda 2, lambda 3, 0, 0, 0, 0, 0, 0 into n, and n is any of these plus minus 1 by root 3, plus minus 1 by root 3, plus minus 1 by root 3, right, and then you further dot with the n, then dot with again plus minus 1 by root 3, plus minus 1 by root 3, plus minus 1 by root 3. And can you see what you are going to get? First, the stress matrix is diagonal multiplied by a vector. What you get is a same vector, but the components get magnified by the corresponding diagonal entries of the matrix, right. So, lambda 1 into 1 by root 3, lambda 2 into 1 by root 3, lambda 3 into 1 by root 3. Then you have to further multiply with the vector itself, and can you see what you get? So, it is going to be simply 1/3 of lambda 1 plus lambda 2 plus lambda 3. is not it? And what is this? This is I 1, invariant 1. So, that means sigma octahedral is simply 1/3 of I 1. So, once we see this in terms of invariance, you do not have to write your matrix in the principal coordinate system. You will have the matrix in any coordinate system, and then sigma octahedral is simply 1/3 I 1, and I 1 is then sigma 1 1 plus sigma 2 2 plus sigma 3 3, right. But remember, the octahedral planes are always defined relative to the principal coordinate system. They are not defined related to a general E 1 E 2 E 3 coordinate system. They are defined relative to principal coordinate system. That is why you get this formula. And now, because I 1 is an invariant, so you could write this in terms of sigma 1 1 2 2 and 3 3. Okay. So, this then becomes 1/3 of sigma 1 1 plus sigma 2 2 plus sigma 3 3. All right. Similarly, what is tau octahedral? So, tau octahedral square. Now, can you recall what that is? That is nothing but sigma into n. So, you get the total traction, take its magnitude square minus sigma octahedral square, that is tau octahedral square. So, what will be sigma times n? You already saw it using the matrix times the vector product, and then you have to take the magnitude squared. That means, you take the individual components, square it and sum it, right. Let me just write it down also. So, this is lambda 1 by root 3, lambda 2 by root 3, lambda 3 by root 3. So, that is the vector, you take its square, magnitude square, and each of them could be plus minus plus minus plus minus depending on what normal you chose, minus sigma octahedral square. So, that is 1/9 times lambda 1 plus lambda 2 plus lambda 3 whole square, right. And can you see what is the first term here? The first term here is simply 1/3 of lambda 1 square plus lambda 2 square plus lambda 3 square minus 1/9 lambda 1 plus lambda 2 plus lambda 3 whole square, right, which you could also write as, you take 1/9 as common, and then you have 3 lambda 1 square plus 3 lambda 2 square plus 3 lambda 3 square minus lambda 1 plus lambda 2 plus lambda 3 whole square. Just work it out little bit more, and you will see that this is equal to 1/9 2 times lambda 1 plus lambda 2 plus lambda 3 whole square minus 6 times lambda 1 lambda 2 plus lambda 2 lambda 3 plus lambda 3 lambda 1. Okay. And that means finally, that your tau octahedral is root 2 by 3 into the thing inside the bracket. And what is that? You see, now it is in terms of invariants. So, that is first one is I 1 square minus 3 times I 2. Okay. So, having written them in terms of invariants, So, now you could also write it in terms of any stress matrix, right, because you know the formula for invariance. So, that is tau octahedral, and you see irrespective of what phase we take. So, you have 8 phases, on each of the phases you have same sigma octahedral and tau octahedral, because you see that plus minus thing cancelled out finally, it is no more showing in the last expression. So, each phases have the same sigma octahedral and tau octahedral, and since they are in terms of invariance, so they are also invariants, right. Sigma octahedral and tau octahedral are also the invariants. Yeah, I guess I missed out this square root here. So, you have to have to the power 1/2. All right. So, that was about sigma octahedral and tau octahedral. There is another small concept of breaking down any stress matrix or stress tensor as a sum of hydrostatic and deviatoric part. Okay. So, let us see what that is. So, you have a stress tensor sigma, we can always write it as one third of I 1 times the identity plus sigma minus one third of I 1 times the identity. Now, this is a very special kind of decomposition, such that the first term is proportional to identity, right, whereas the second term is such that its first invariant is 0. So, if I call this as some sigma hat tensor and then I try to find out its first invariant, okay. Can you see what is its first invariant? Let us do a side calculation. So, first invariant I 1 for sigma hat, what is that going to be? First invariant is simply the sum of the diagonals, and sigma hat has got 2 terms here. So, I 1 of sigma hat is simply I 1 of sigma minus I 1 of the other one, right. So, this is equal to I 1 of sigma minus I 1 of the other component, one third I 1 identity. So, we have I 1 of sigma minus one third I 1 is a scalar quantity which is going to come out minus one third I 1 times the I 1 of identity. What is the I 1 of identity? First invariant is sum of the diagonals, identity has 1 on the diagonals, sum it you get 3, right. So, 3 cancels. So, this 3 cancels with this number and you simply have I 1 minus I 1 equal to 0, right. So, the second term has got 0 first invariant, right. So, it has first invariant 0, and that is why it is called deviatoric part of the stress tensor. The first term is proportional to identity. So, it is called the hydrostatic part of the stress tensor, because the hydrostatic stress is always proportional to identity, right. So, this is called hydrostatic part whereas this is deviatoric part. Another reason to call it deviatoric is because this part has got 0 first invariant. So, it will be possible to choose a coordinate system such that this deviatoric part, when you write it in the matrix form, will have all the diagonal entries 0. So, let me write here. If I 1 equal to 0 for a tensor, there will be a coordinate system such that the matrix form of this tensor A. So, this tensor is A, will have 0 on the diagonal and non-zero on the off diagonal. So, if you have such a stress matrix which has 0 on the diagonal, that means it has no normal traction on those 3 planes and it has only shear traction. If you draw the cuboid corresponding to this matrix, the faces of the cuboid has only shear component of traction, right. So, whenever you have only shear traction, then it will try to distort the cuboid, keeping the volume fixed, but it will try to change the shape of the cuboid, try to distort the cuboid. So, that is why it is called the deviatoric part of the stress tensor. So, this matrix, the corresponding cuboid will only have shear tractions on their faces. Okay. And it turns out, if you only have shear tractions on the faces, then when the cuboid gets distorted, because the shear traction is there, it is going to get changed, right. The changed cuboid or the changed shape will preserve its volume. So, volume will be preserved, but the cuboid gets distorted. All right. And this stress matrix that you see here, it is also called state of pure shear, right, because there is only shear component, there is no normal component. So, this is also called state of pure shear. See, contrast this with the first term here, the hydrostatic part. The hydrostatic part has only got normal component of traction. So, think of the cuboid with only normal traction acting, right, and it is the same on all the faces. So, such a traction, whenever such a force acts on the cuboid, it will only try to change the size of the cuboid, it will not distort the cuboid, right. It will let the cuboid remain a cuboid, but just change the size of the cuboid. So, this part is responsible for volume change. Okay. So, this part is then responsible for volume change. Okay. So, basically you can always decompose a stress tensor into two parts, hydrostatic part and the deviatoric part, and we say that the hydrostatic part is responsible for volume change, whereas the deviatoric part is responsible to distort the body. The deviatoric part does not change the volume, but it changes the shape or distorts the body. The hydrostatic part changes the size, changes the volume, the second part does not change the volume. Okay. All right. So, that is all about stress. There are some small concepts still remaining which you will see through tutorials, but this is all. In the next class we will learn about strain. All right. Thank you.